Yeah, so I'm a theoretical physicist, and most people shrug when they hear that and they say I didn't do well in that. I assure there are no equations and only cartoons to give you a general idea of what to do. Okay. So imagine that you're a molecular biologist, and then you're interested in how RNA strands fold in proteins. This is a very tricky question, and a very numerically intense one to solve, giving a headache to molecular biologists all over the world. But basically you can categorize problems into two categories. Things that are easy, like having safes with a bit of knob on them. If you add more safes with a knob, you just need to add a little bit more time to solve all of them. However, if you put all of those little knobs on one safe, you need to get them all right to solve the problem, and that's more like the RNA problem. So if you add just one more knob, the problem becomes a multitude more difficult. And if you add more knobs and more knobs and more knobs, well, eventually you run into a monster problem that you can't solve in reasonable time. And that's where the quantum computing comes in, because we can use physical processes to circumvent these problems in certain cases. So we can, for instance, solve our monster problem sometimes. Now, no one knows today what a quantum computer looks like. There are several actual examples and some fictional examples of what these could look like. So we're free to explore what we want. And we're looking for something that lives in two dimensions. And it's called a topological quantum computer. And what we really do is we braid special types of particles around, and that makes up our computation. Now these are found in two dimensions. But two dimensions is not as special or strange as it might sound first. Many things effectively live in two dimensions. For instance, the surface of a table is two-dimensional, if you just care about where you place things. So when we're studying electrons in two dimensions, they're just confined to two dimensions. They're not actually two-dimensional. And the way you do that is you take two metals, you slap them together, and you trap the electrons inside. That's the green blobs. Then you cool this to almost absolute zero temperature, and you put on a strong magnetic field, 10, 20 Teslas, it burns your credit card straight out. And then you can perform measurements, something like measuring the resistance as a function of the magnetic field. And you find that the resistance doesn't actually depend on the strength of the magnetic field. It's so precise that you can define the resistance up to 12 significant digits. That makes this one of the most accurate experiments in the world. And it amounts to measuring the circumference of the Earth to a precision of just a fraction of a millimeter. You can't really do that in the real world, of course. We're interested in this because here the electrons behave strangely. So normally, if you take an electron, you zoom in, it's just an electron, no more structure. But in these systems, if you take an electron, you zoom in, it looks like a scatter plate separated into quarters of electrons, special types of particles. And we're interested in their properties. Normal electrons don't have a memory. If you take two electrons, you move them around, they don't really know that you did anything. It's the same as doing nothing. But if you take these quarter particles instead, they do have a memory. So if you do the same thing with those quarter particles, they know whether you did nothing or did this little dance with them. So you can store information this way. If you can determine whether you did nothing or something, that's kind of a computation, right? You can store information this way. So you can use the braiding of these quarter particles to store information and process information. And that's a computer. And this is a quantum computer, because you use the forces of quantum mechanics to implement it. But quantum computers are very, very delicate. Got caught up the wrong way anyway. It's like a Ming vase. And I mean, if you look at it, it'll break. So you have to shield these things off. Someone looks at it, it breaks, your complete computation is just worthless. You might as well not do anything at all. And it's really noise that does this. Noise in the form of other particles that sneak in to your computation and braid with the particles that you want to braid, creating extra knots in your little braiding, for instance. But you can get away with this, you can get around this by cooling the samples to almost absolute zero temperature. And if you manage to do that, all of those particles that you don't want there, they just get frozen out. They can't move, they're not in the way, and it makes the computation noise-free. So there's a threshold, but it makes it noise-free. And that's what we like about it. So we kind of know where we're going. We have a few steps on the way, but we've really only begun this journey, and we have lots of things to do on the way. Thank you very much.